In a kinematics problem, when an angle is given to solve for any parameter, may it be displacement, velocity, and acceleration, polar coordinate system can be employed. Welcome to Dynamics of Rigid Bodies. The first situation has a car traveling horizontally at a velocity of 100 kph. At 60 degrees, we are to determine the radial velocity in meters per second and transverse velocity in degrees per second. An illustration for the problem shows that at a specific point of origin, a car is moving in a 30-meter gap from the origin. At the instant that theta becomes 60 degrees, we are to determine the components of velocity, and those are radial velocity v sub r and transverse velocity v sub theta. The radial component is taken as an extension of the line from the origin to the car. The transverse velocity is drawn perpendicularly from the radial axis. After identifying the unknowns from the illustration, we can start computing. First, convert the velocity into meters per second to have it aligned with the required. So 100 kph is multiplied by 1000 meters per kilometer and again multiplied by 1 hour is to 3,600 seconds, resulting to 27.778 meters per second. We can then compute for the radial velocity r dot, which is also taken as v sub r, and that is taken as the velocity v multiplied by the cosine of 60 degrees. That is 27.778 cosine 60, taken as 13.889 meters per second. Let's continue solving the components from the illustration. V sub theta is directed towards negative theta axis, so V sub theta is negative V sine theta, which becomes negative 27.778 sine 60 degrees, computed as negative 24.056 meters per second. The transverse component is a little more complicated than radial. From physics, remember that arc S is taken as r theta. So by differentiation and radius as constant, we get V sub theta equal to r times theta dot. Theta dot is the transverse velocity, now taken as V sub theta all over radius r. As we have already determined V theta, we can now look for r. Radius is taken as the distance from the origin to the particle at specified angle. So using trigonometry, sine 60 degrees is computed as the adjacent side 30 meters all over the hypotenuse r. So the radius r is solved as 30 upon sine 60 degrees, or that is 34.61 meters. With r and v theta already known, we can finally compute for theta dot as negative 24.056 divided by 34.61, which comes out as negative 0.694 radians per second. However, the problem requires transverse velocity in degrees per second, so convert the result by multiplying the conversion factor 180 degrees is to pi. giving the value of theta dot as negative 39.788 degrees per second. Example 2. A jet plane flying at a constant speed v at an altitude h equals to 10 kilometers is being tracked by a radar located at station O directly below the line of light. If the angle theta is decreasing at a rate of 0.02 radians per second, when theta is equal to 45 degrees, determine the value of r double dot at that instant, and the magnitude of the velocity v of the plane. With the given parameters shown in the illustration, and only the transverse velocity as 0.02 radians per second, we would need to find more parameters to complete the equation v theta is equal to r times theta dot. V theta is taken from the components as v sine 45 degrees. Radius r is also taken just the same from the origin to the particle at the angle stated. Using the triangle as shown, sine 45 degrees is 10 kilometers all over the hypotenuse r. Radius is then computed as 10,000 all over sine 45. That is 10,000 root of 2 or 14,142.14. Plug these parameters into the velocity equation and have v sine 45 equal to 10,000 root of 2 multiplied by 0.02, then manipulate the terms to have 400 meters per second. The next requirement is to look for acceleration. But since it was cleared out in the problem that the plane is flying at a constant velocity, we can deduce that acceleration is 0. That means that the radial and transverse components of acceleration are also 0. So to solve for r double dot, we take the equation of radial acceleration, which is r double dot minus r times the square of theta dot, which is again equated to 0. We get r double dot equal to r times the square of theta dot, and that is 10,000 root of 2 times the square of 0.02, simplified as 5.66 meters per square second. The next example uses an amusement park ride consisting of a revolving chair with an arm of 4 meters, angular velocity of 2 radians per second, and angular acceleration of 0.25 radians per square second. We are to look for the radial and transverse components of both velocity and acceleration of the particle. Start with the radius equal to 4 meters. If we differentiate radius, we take r dot, and since 4 is a constant, we get r dot equal to 0. R dot is also radial velocity v sub r. Also, r double dot is taken as 0. For transverse velocity v theta, we use r times theta dot, and by simply plugging in the given parameters, we get 4 times 2, or that is 8 meters per second for the transverse component of velocity. The radial acceleration is solved from the formula. R double dot is solved as 0 minus r, which is 4 times theta dot, which is 2. So we compute the radial component of acceleration as negative 16 meters per square second. For transverse acceleration, it also has its own equation, which we can simply plug parameters as 4 times 0.25 plus twice of 0 times 2 or 1 meter per square second for the transverse component of the acceleration.